And microplastics or plastics in general, a large amount of them, 80% of them, come from land-based or inland sources, meaning inland streams and river systems. So thinking about marine areas, if microplastics are entering marine systems, I've done work looking at how they can impact different types of organisms as far as shrimp, oysters, and I even have work right now looking at dolphins, microplastics within dolphins in South Carolina coast. Within freshwater areas, that can come from the release within wastewater effluent. Also, degraded infrastructure, sewage infrastructure, where there's leaky pipes that can leach out not just microplastics.
Before we get started, I have a quick favor. I've been self-funding the Finding Genius podcast for 5 years now. I've done over 3,000 episodes. And as you can see on YouTube, we're up over 1 million views on the channel, which is fantastic. The next thing I really want to push on is to get up to 10,000 subscribers, because once we do, we'll be able to put a donate button, and we'll be able to solicit donations to help keep the podcast running and to also get the Finding Genius Foundation moving along. We have a big project studying anxiety, depression, and PTSD, and working on a product to help people overcome these problems, because I've seen them explode recently after the last 2 years of the whole virus situation. So if you would, please subscribe to the podcast. That would help us tremendously. Give us a thumbs up, and check in the description for Buy Me a Coffee. It's about $5. If you could buy me a coffee, I'd really appreciate it. It would help keep the channel going, and I love coffee. Thank you.
Forget frequently asked questions,
common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
go above and beyond.
They become very good at what they do, but only
0.1%
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast
with Richard Jacobs.
Hello, this is Richard Jacobs with the Finding Genius Podcast, now part of the Finding Genius Foundation. I have Austin Gray. He's an assistant professor of biological sciences at Virginia Tech. I'm going to talk about his work with microplastics and nanoplastics and aquatic toxicology. So, Austin, thank you for coming.
Oh, thanks for having me.
If you would, tell me about your background, and then let's talk about the research you're doing right now.
Yeah, so just briefly, from North Charleston, South Carolina. I'm the youngest of 5 boys, and I started my research journey back at the Citadel Military College of South Carolina. I started doing research at 19 under the lab of Dr. John Weinstein. I stayed there for my master's. Afterwards, went to the Medical University of South Carolina for an NIH post-baccalaureate program. Then did my PhD at UNC Greensboro, my postdoc at Duke University, and now at Virginia Tech as a AP, as I call it, assistant professor. And my research is mainly focused on basically understanding how different types of emergent contaminants affect aquatic ecosystems, and that could be plastics, microplastics. I do a lot of personal care products work with green products. Also thinking about pharmaceuticals. Large part of my recent research has been focused on pharmaceutical pollution, mainly antibiotics as well, with microplastics. So that's the main cuts of my lab. And again, we really focus on utilizing ecological and physiological approaches to understanding the consequences of these contaminants within aquatic ecosystems.
Okay, what kind of ecosystems are you focused on? I mean, there's a lot of different aquatic lakes, rivers, streams, oceans.
Yeah, so...
And then what kind of contaminants?
Yeah, so when I was in Charleston, because we're on the coast of the East Coast, Southeast, a lot of my early work was focused on marine, more coastal, so estuaries, tidal creeks, and also open ocean. And then as I transitioned throughout my PhD and postdoc, it transitioned over into streams, more freshwater systems. And now as a AP, it's both. I get to kind of dabble in both worlds, understanding microplastics and pharmaceutical pollution within freshwater and marine systems. And I do that largely because they're all connected. The interesting thing about water and how water moves is a freshwater system can definitely influence a marine system depending on how basically what kind of contaminants are entering in freshwater areas. They ultimately end up in the coast. So being able to study both is really one of those really cool niches of my research program. Is I'm not constrained to just doing one. I could do both.
Right, but what kind of contaminants? What sources? What's your model system, or what are you studying in particular?
So when thinking about microplastics, it can vary when thinking about marine. So focus on marine areas. We look at basically inland areas that receive or drain into tidal creeks or estuaries. And microplastics or plastics in general, a large amount of them, 80% of them, come from land-based or inland sources, meaning inland streams and river systems. So thinking about marine areas, if microplastics are entering marine systems, I've done work looking at how they can impact different types of organisms as far as shrimp, oysters, and I even have work right now looking at dolphins, microplastics within dolphins in South Carolina coast. Within freshwater areas, that can come from the release within wastewater effluent, also degraded infrastructure, sewage infrastructure where there's leaky pipes that can leach out not just microplastics, but also antibiotics, other pharmaceuticals. And when I think about personal care products, a lot of the work that I've done with personal care products covers both marine and freshwater systems, mainly green products, products that are marketed as better for the environment or eco-friendly, and testing whether or not those claims are true. A lot of times we see a lot of greenwashing saying that these products are better for the environment, more degradable. But in research that I've been doing within my laboratory and continued research, we've shown that these green products, in most cases in regards to mortality, are more toxic even after degradation than conventional counterparts, meaning that if you were to go to the store and buy a green laundry detergent, if you were to compare that to Tide and Gain, which we traditionally buy, the Tide and Gain products are typically less hazardous than the eco-friendly products.
Well, okay, this is interesting. This may be a part of the law, but so if I have a product and it has like, I don't know, 5 substances in it, 5 chemicals, whatever they are, A through E, if they break down faster than my competitor's product, do I have to care or worry, or am I liable for what they break down into? Or is the fact that they break down, let's say, faster than my competitor's product is all I need to say and claim that mine is more biodegradable? Does that word and term hide that? And again, are the degradation products looked at, or is it just they fall outside of the rules and the language that governs these things?
Yes, they typically do. They don't, for these claims of eco-friendly or green chemistry, there's 12 tenets or 12 principles, and these things don't have to be proven or tested before being slapped on a label. They are kind of, again, thinking about advertising and I'd say greenwashing. These claims are largely put out there and they aren't ever really tested. So there's not much need to look at, or most corporations don't typically look at these claims or test them all out before they slap them on the label. They may design them in the idea being that they're more degradable, but once they're mixed with other compounds and mixtures, their effects are typically not really known because most of these products aren't tested on animals and they aren't assessed in regards to truly how it affects non-target organisms in the environment.
It's terrible. Yeah, that's really crazy. So if I have, again, chemical A that breaks down to something horrible, and you have chemical B that breaks down a lot slower but into something less harmful, I'll still, like on paper, be able to claim that, you know, mine is more, let's say, environmentally friendly or more biodegradable, that kind of thing.
Yes, and even looking at recent policies by the EPA, they are transitioning out of live animal testing, and there's one aspect where there's a benefit, but also, again, if you think about marine or aquatic invertebrates that are really sensitive that aren't assessed in a laboratory, when those products go into the environment, those are the organisms that are directly affected because they reside in these receiving bodies, whether streams, rivers, or estuaries.
Is there a language or a name for the first set of degradation products versus subsequent ones? Like, has anyone followed these chains of degradation, and how many forms I know it depends on the chemical, but, you know, again, is there even a naming convention for the first set of products, the second set, the third derivative set? And does anyone even look to, even the first set, probably they don't, but beyond that, they probably certainly don't, right?
No, yeah, I'd say it's really difficult to really identify these degradation or these metabolites or these transformation products because based on the chemical structures, a lot of these can happen in ways that we don't have standards for. So when we think about analytically, when we want to look at target compounds, we have a known substance that ultimately is assessed and we know the mass, we know the chemical structure, but when it degrades or becomes a metabolite, its chemical composition changes completely, which makes it really difficult for a scientist like myself to pinpoint these changes. And we have a lot of work developing within non-targeted or high-resolution mass spectrometry, which is basically doing non-targeted analysis, where we can look for signals and how they change. But even with those approaches, it makes it extremely difficult because we don't have a reference to go off of.
Before we continue, I've been personally funding the Finding Genius podcast for 4.5 years now, which has led to 2,700 plus interviews of clinicians, researchers, scientists, CEOs, and other amazing people who are working to advance science and improve our lives and our world. Even though this podcast gets 100,000 plus downloads a month, We need your help to reach hundreds of thousands more worldwide. Please visit FindingGeniusPodcast.com and click on Support Us. We have 3 levels of membership from $10 to $49 a month, including perks such as the ability to see ahead in our interview calendar and ask questions of upcoming guests, transcripts of podcasts you're interested in, the ability to request specific topics or guests, and more. Visit FindingGeniusPodcast.com and click Support Us today. Now, back to the show.
Yeah, I was thinking also in terms of microplastics. So if we have some that comes from land-based sources, they go into a river, it's mostly fresh water. Now it starts to go to its outlet. Maybe now it goes into an estuary. Now you have brackish water. The salinity is much higher. Then eventually maybe it goes into the ocean or the Gulf. Salinity now is even higher. The pH is changing. The conditions in which the microplastics are interchanging, the fish and other fauna and flora and stuff are changing. Have you seen any major alterations in how microplastics behave and degrade and accumulate as they transition, let's say, from a freshwater to a saltwater regime?
Yes, this is actually new data from my laboratory, but going back to when I was in Charleston at the Citadel with Dr. John Weinstein, we looked at how macroplastics, so large plastic items, degrade within a salt marsh environment, and we wanted to track it to see exactly. Because we think about plastics, people think the misconception with plastic is that, it takes hundreds of thousands of years to break down or degrade, but really that's hundreds of thousands of years to be mineralized or removed. What we aren't accounting for is the fragmentation rate, which is what produces microplastics. And we found that within a salt marsh environment, it takes 8 weeks to start producing microplastics. And with my recent studies that I've been doing here within forested and urban streams, we found that within stream environments, it takes as little as 2 weeks to start producing microplastics. So we're actually seeing faster fragmentation within inland streams than we do within coastal estuaries.
Interesting. Yeah, I've had a lot of questions around this. I've talked to a lot of microplastics people. I pictured, a typical soda bottle. And when it produces microplastics, I pictured that the whole soda bottle will be composed of like little pieces, some maybe a quarter of an inch long, some smaller, and there'll be tons of microplastics mixed in. And then I said, wait a minute, what if the real model instead is I look and I see the bottle in the water, maybe there's a hole in it, but it looks mostly intact. Mm-hmm. And what I don't see is all the microplastics that it's releasing, maybe at the site of the rupture. Which one to you is more representative? I guess for the 2-week time scale, what people could expect to see is most of the macro is visible, or all the macro is visible, but the microplastics are invisible, but they're there already.
Yes.
After a couple of weeks.
No, exactly. It's, again, like you mentioned, more the latter, where, again, imagine you go into a creek or you go into a stream and you find this bottle and it looks intact, but there could be some mechanical, like physical abrasions that have happened because of its transport, because of coming in contact with not just sediment, but rocks or cobble, root structures. And that physical abrasion is going to cause some kind of fragmentation to an extent that's producing microplastics. And that's largely what it is. I mean, if you were to walk into, like, say, a beach, and you go to the beach and you see a styrofoam cup, if you pick up that cup, it's not going to break apart, but you also notice little white flakes on your fingers, and you're wondering what those flakes are. That is also microplastics.
So it sounds like it would make sense to pay a lot of attention to macroplastics in any body of water and get them out. If I have, I'm in Austin, Texas, Lady Bird Lake, I walked it and all that, there's all kinds of plastics on the quote-unquote shores of the lakes. If they went and every 2 weeks skimmed out as much as they could, that would probably dramatically reduce the source of microplastics for the lake, because they're not sitting there for months and years. And, one plastic bottle, I would think, could spew out billions of microplastics over time. So yes. I would guess that it would be a good strategy to do this, is get rid of the macro as often and as fast as you can, and that alone may reduce the load of microplastics dramatically.
Yes, so there's, I guess, 2 different approaches to that where, yes, if you remove the macro, because what we know is we have primary and secondary microplastics. Primary being those that are manufactured commercially to be in personal care products, but the United States in 2018 passed a microbead ban, removing those from personal care products. But the real culprit is secondary microplastics, which is microplastics that fragment from larger plastic items. So these big plastic items that are out there due to waste or accidental loss or intentional littering, those are the main culprits producing microplastics. And that's a big issue right now is, we clean it up, but also we know that microfibers, which are another form of microplastic or category, those are also coming because of laundering. So if you wash a nylon fleece, we initially thought that if you wash a nylon fleece, which nylon is a plastic polymer, if you wash that for one wash cycle, it would be 1,700 particles released. Now we know that that was a vast underestimation. That number is really 100,000 particles from one nylon fleece in one wash cycle. So imagine, again, depending on where you live at, and if you live in a more northern area where it's cooler or colder, and you have a lot of people in high density washing a nylon type fleece, how many microfibers are going out there and they aren't really captured through wastewater treatment facilities? So they still end up going back into the environment in that amount. And so while microplastic debris is one way to combat it, we also have these other types of sources beyond just that. Again, going back into laundering and also tire abrasion. We know that tire wear particles are also microplastics, and tires are sources of microplastic pollution. So tire tread, when tires wear down. These are all different schemes outside of just macroplastics that are contributing to the continual input of microplastics within our aquatic systems.
Yeah, this is a really, really difficult problem. Have you looked at, let's say, again, a plastic bottle that's blown open and has released microplastics? If you look near the site of rupture, will you see preferential leaching of the plasticizers and the colorants and all that stuff? Or will you see, so again, will you see like raw exposed polymer backbone at the rupture site? Or will you, again, and is there preferential leaching of the additives that go into various plastics, dyes, plasticizers, flame retardants, all that? Like what do you think happens in this leaching and the creation of microplastics? What do they look like?
Yes, so there are different types of studies that have been done. I do a lot of analysis with one of my instruments, the Raman mass spec, to look at these microplastic particles. And even with the microplastic particles, you can see additives, or you can get signatures of different additives, heat stabilizers, plasticizers that can come off, even dyes. But these are fragmented off of a macroplastic item, showing that while there may be some degree of leaching at the fragmentation site, it still has signatures even with the microplastics. So it's not as if when you see fragmentation on a big, say a macroplastic or a bottle, that you see backbone or there's nothing left. I think a lot of these things really persist much longer. And again, it's just gradual over time.
But do you think there's a preferential leaching the additives, or the backbone degrades and everything comes with it? Like, has anyone studied structurally what happens to a given polymer as it breaks down?
Yes.
What does the interface look like, the breakdown interface?
Yes, so we've done some work with that as well. And one thing that we noticed that happens is somewhat of if you think about a lot of plastics, that they have to resist heat. They have to resist types of alteration. So there's a lot of what we saw initially was this delamination effect, where because of the biofilm development, because of the water flow, we saw this delamination where the lamination or the external part of the macroplastic started peeling off, which then led to the structure being compromised and then more degradation or more fragmentation.
Yeah, in terms of the microbiome, again, if a plastic starts in a river, it would have a certain microbial attachment because it's freshwater, which would change in the brackish, which would change again in the ocean.
Mm-hmm.
So I guess that plastic would experience like at least three very different microbiomes throughout its travels. And I guess each preferentially would eat away at the plastic in a different way. Maybe that's why you're seeing faster degradation in freshwater versus, let's say, saltwater. I don't know. But has anyone looked at that?
Not directly, but there have been studies that have looked at biofilm formation. And a lot of things what we've seen with the biofilm is when the biofilm is established, a lot of times that takes out the implications of, say, UV rays causing degradation, because the UV rays can't penetrate to the plastic because they have this biofilm develop. But as a biofilm develops, it's a really complex community structure of microbes and bacteria that in some cases, some may be actually utilizing those plastics as a substrate or some kind of food source and utilizing that for their own growth, which can then lead to fragmentation or degradation to the macroplastic item as well.
So what kind of questions are you working on that are really I mean, it seems like they all are. What's your goal with your research? What are you trying to understand, or are you trying to create a process by which these effects can be mitigated of the microplastics, or it's just let's just see how they're affecting the environment, what happens to them, and then from there the answers may come on what to do about them?
Yes, so it's a mix of all of that, I would say. A lot of my main goals is really trying to bring awareness to environmental health in emphasizing that environmental health and human health are intertwined. The way that we impact the environment has a direct implication on us. If we utilize, say, plastic items and we improperly discard them and lead to a lot of litter within aquatic systems, those microplastics are going to end up in waterways where, if you live on the coast like I did in Charleston, you rely on seafood. Seafood is a major part of the economy. If we see that microplastics have negative implications on commercial seafood items, say shrimp, crabs, oysters, shellfish, mussels, then that's going to have a direct impact on the economy. But also, if these microplastics are transferring or being a vector of other contaminants that can be carcinogenic, then we're exposed to that as well, and that's going to affect us at some point. A report just came out last March that for the first time we reported microplastics in human blood. And because microplastics are reported in human blood, you can imagine nanoplastics are as well. And there's so many unknowns associated with that, where these micro or nanoplastics can translocate into our cells. They can cause oxidative stress. They can maybe change gene regulation, resulting in more mutations or cancer. And so that's just one example of how us as humans and our activity can influence the environment, which can in turn influence us. And the same scheme goes for pharmaceuticals. We use pharmaceuticals readily because of our healthcare system and our need as we increase our populations. And when we use pharmaceuticals like antibiotics, our body doesn't break all of those down. Roughly only 10% of it's ever broken down. So 80% of it goes into the environment in active form, because in our waste, we don't, again, that's where it resides, in our waste. And in wastewater treatment facilities, they aren't equipped with the instrumentation to remove these contaminants. So within effluent, they go right back out there into the environment. And this is why we see incidences of antibiotic-resistant genes being spread, and why it's hard to combat certain infections, because these bacteria have already been exposed at low dosages to these pharmaceuticals, so they're resistant. And so, again, thinking about the age of coming out of COVID or dealing with COVID currently, we're dealing with virus in that case, but what if it's a bacterial infection that is resistant to most antibiotics? That would decimate our public health infrastructure. So it's really bringing awareness to that aspect, that environmental health and human health are intertwined.
Yeah, no, it makes a lot of sense. Another question is, I've heard, it takes, like you mentioned this earlier, it takes thousands of years for plastics to, quote unquote, break down. What does breakdown mean?
Yes.
If I have a bottle with a hole blown open blown into the side, it's not broken down. But if I have a million pieces of a plastic bottle that are a quarter inch wide, is it broken down? Or is it broken down where there's no visible plastic bottle at all? And what's the significance of the term broken down? It doesn't really seem to be useful.
Yes. So, and that's a big misconception with, again, the terminology, where when we say a plastic item lasts for hundreds of thousands of years, what they mean is really it takes hundreds of thousands of years for it to mineralize, the mineralization. And that goes back into thinking that plastics are just another type of carbon, another recalcified form of carbon. It's derived from petrochemicals or oil-based polymers. And so when we talk about mineralization, that's the formation of this product back into water and carbon dioxide. And that's what takes hundreds of thousands of years.
So is it even useful to say that plastics take thousands of years to degrade? Because in the public mind, I would guess that they would just picture the item sitting there, maybe covered in dirt, or, it's filthy, ragged, torn, but it's still there.
Mm-hmm.
And then somehow thousands of years later, it's completely gone. But who contemplates what it means to break down and how long it takes. And
yes. And that's, and that's a big, again, how we speak to the public about our work in doing plastic research, that it's hundreds of thousands of years to be mineralized, to be completely removed, but not broken down. Because as we show within the work that I've done, the breakdown process or the degradation process happens within a week scale, not hundreds of thousands of years.
Have you profiled a given object, for, 6 months, let's say? Like, I don't know if anyone's done this. I've asked. I don't think anyone has. I keep referring to plastic bottles. I know fibers are very prevalent too, but let's say you take a sweater and you have a washing machine and a dryer, and you hook up instrumentation to them, and you look at like the lint trap of the dryer, and you look at, what's in the washer, the liquid, and, over time you wash this sweater, once a week for 6 months or a year. Let's say you even wear it, but you monitor the effluent of the washing machine and the lint trap on the dryer and the hair effluent. What would you see over time? Would you see more and more fibers over time, or less and less? Or has anyone looked at a profile of how, for instance, an object like that would degrade and break up?
Yeah, so I'm not 100% aware of any work that has done that deliberately, and there's probably been work and I just haven't come across it. But from my own opinion, I would say that you would see a continual or an increased release of these fibers or particles over time. The more you wear something, the integrity is compromised. The more you wash it, the more you go into the environment, and you have different types of environmental factors like air, wind, traffic that can release particles. Is going to be a continuous release over time.
Okay, would it be useful to do such an experiment and see the degradation profiles, you think?
Yes, and again, I think that's one thing that's like is likely might have been done. It just hasn't. A lot of these ideas or a lot of these concepts are things that maybe in theory or in practicality, but also in the best way to control it in the laboratory or based on research agendas or initiatives. Maybe it's been done, and that just hasn't been something that I've thought of to do. But the wheels are turning right now. As you mentioned that comment, I'm like, oh, that would be something I can track over time.
I know you can't do everything. Yeah, just figured I'd bring up some ideas. What do you think needs to be done still that will be incredibly useful to your research and to overall microplastics research? Because it seems like it's a very active field now, but it also is a very young field. And, all the people I've spoken to, not a lot is known. Sounds like you know a lot more than some. But what needs to be done? What kind of research do you think needs to be done to like elucidate important things that would help us understand microplastics and mitigate them?
Yeah, and I think the first thing goes back into our sustainable usage. I don't think we're at a point in our society where we can ban plastics. I think that's just not realistic, depending on, again, you think about how widespread and used plastics are and how ingrained they are into our society. It's not so much that we can just ban plastics. I think we have to really emphasize and practice sustainable usages, and that goes back into recycling. If you think about, so plastics have different SPI codes, it's typically 1 through 7. And out of the 7 SPI codes, only 2 of those SPI codes or plastic polymers are easily recyclable. The rest may be specific depending on what facility you go to. The others may never, like polystyrene, you can't recycle it because once you heat it up to a high enough temperature, which is needed for remolding, it's no longer good anymore. So utilizing plastic polymers or emphasizing plastic polymers that can be recyclable and ingraining that into our society, mainly with, again, the next generation, so that we aren't just creating a lot of merchandise or products with plastics that even if we did recover it, we can't recycle it. It would still go to waste. It would still go into a landfill. It would still be a detriment to the environment. And that's something that I don't think is really talked about enough, is the fact that, again, we have very few polymers that can actually be recycled. And I think a lot of the public assumes, I know I did growing up, you see a receptacle, you see a recycling bin, you put a product in there, plastic, whatever, you assume that it's going to be recycled, reduced, reused, and you're helping the environment. But really, it's only 2 polymers that actually do that can actually be utilized that way.
Yeah, I mean, you're right. There's no way to just ban this stuff. It's being used. I would think an 80-20 approach, 80% of the results come from 20% of the inputs, like a Pareto approach might be the cleanest way to help this stuff. What would reduce, the plastics that are the most, well, first of all, which ones are the most harmful and what context, and what would reduce them 20%, 50%, maybe even 80%. 100% is just not going to happen, it sounds like.
Yeah.
I would think that kind of approach would work better.
Yeah, and putting a lot of emphasis on the corporations that produce these plastics, that if you're going to produce X amount of plastics a year, you should be also accountable and responsible for recycling or recapturing a certain amount, like you mentioned, a certain percentage. That if you produce 100 tons of plastics a year, then you should be responsible for, say, recycling or recovering 80 tons of that plastic, because those are important. That's important standpoints of, again, from the beginning to the end, holding them responsible, because it's similar to like the carbon footprint. You go to a regular person or anyone within their home, depending where they live, they're not concerned about their plastic bag as much as they should be, because that's just not they got enough things going on, people in their everyday life. So the emphasis has to be put on the corporations or the industry that produces the plastics, because they're the ones that, again, they're responsible for it. They're the ones using the resources for that. And if they aren't held accountable, then I don't think it's fair to hold the individual consumers accountable or responsible as well.
Yeah, true. So what are, I don't know, over the next year or so, are there any interesting experiments that you're working on that you're excited to see the results of that you could talk about?
Yes. So I have a 5-year grant right now with NOAA, and it's looking at microplastic contamination or presence within the intestines of stranded dolphins, bottlenose dolphins. These are apex predators, and these are dolphins that end up stranded, meaning they wash up dead on shore. And we're taking these dolphins, taking their intestines, digesting them down, which sounds really fun, digesting the intestines down and looking at microplastics. And we're tracking that and comparing that with what we're seeing within Charleston Harbor, because Charleston Harbor, as I mentioned, we were doing this work back in 2013, is one of the most well-documented sites of microplastics globally. We've looked at it in surface water, sediments, sea surface microlayer, shrimp, oysters. 99% of the fish in Charleston Harbor have microplastics in their bodies. So now we're scaling that up and looking at dolphins. And we found so far within our first year, this was work that has largely been led by Bonnier et al. At NOAA, and we found an average of over 1,400 microplastic particles per animal, and we looked at 14 animals. So these numbers are really high, and we aren't even going to the smallest size fraction that we could be looking at, and we're seeing levels this high in dolphins. So monitoring that over 5 years will really tell us, for an apex predator at the top of the food chain within that ecosystem, how microplastics are entering or working their way up into the top level. And I think that's a really interesting study for, again, monitoring, for seeing how it may affect different organisms, and seeing just how far the pollution goes within the ecosystem, from a shrimp ingesting a plastic to a dolphin having plastics in their body.
An organism that ingests the microplastic or breathes it in, I would think the breathing it in, at least probably the 1 micron size, I believe, is the sweet spot, unfortunately, for getting lodged in tissue and causing problems. And maybe the nanoplastics are small enough that they pass through an animal more often than microplastics. Don't know, but have you seen, is there any size regime that is particularly troublesome to living?
Depends on the organism, and what we've shown. I did some size and shape dependent work back in Charleston looking at mainly shrimp, so I can only speak to shrimp. And we exposed them to 3 different shapes, beads, fragments, and fibers in different size fractions from 35 micron up to 165 micron. And we assumed for the beads, we would see like the bigger the plastic, the more it would cause physical or some kind of damage. And what we found was that the small particles that were 35 to 50 or 65 micron passed right through. Those that were too large were either taken and then removed immediately before it could be ingested. But the intermediate size fractions, the ones that could be ingested, but also happened to be too large for the GI tract, but we saw cause, one, external residence time, meaning that the particle stayed in the body of the animal roughly 48 to 72 hours, where typical food particles take 3 hours to pass through. This time was extended to 48 to 72 hours, meaning that they have a gut full of plastics, but they're getting no nutrients from it. And along with that, the plastic, as it goes down the GI tract of the shrimp, was causing physical abrasion inside, which led to internal bleeding, and we saw high mortality. And we also saw the similar trend with fibers, but the fibers were smaller. And so if you think of small fibers, when fibers get together, they aggregate together. They form these irregular clumps and shapes. So when they were consumed, they formed these irregular, jagged, rigid shapes that did the same thing as they passed through the gut tract, meaning that there are certain size fractions, depending on the intestinal or the GI tract of the organism, in which microplastics can be physically harmful.
What a mess. Are you able to see down to the nanoscale? Or, I mean, I know there's tons of complications with that, but is there any spectrographic methods that can see nanoplastics?
So there's certain instrumentation that can detect nanoplastics, but as far as like seeing, you need really high-powered instrumentation like microscopy. I have a Raman mass spec that can get down to 100 nanometers, but the samples that I've looked at thus far have been roughly, the lowest I've looked at has been around 20 micron.
Oh, why not try looking at the nanometer scale and see what you see?
I haven't gotten anything to be that small. That's the main reason for that.
Oh.
Most of the targets that I've been given or gotten from the environment are typically around that range of 20 to 30 micron, but I haven't even thought about like trying to purchase an individual or looking at a bulk of nanoparticles and then observing. But I do know the instrument itself gets down to roughly, again, 100 nanometers.
Well, couldn't you create them easily in the lab? Like, why not have, again, a sweater and throw it in some water and sample the water and they'll, detect for nanoplastics if they're there, then try to sample it.
It's a matter of visually observing the nanoplastic to get it to the instrumentation. And yeah, there's nothing I have or nothing that I can use at the point to identify or isolate a nanometer microplastic and analyze that on the instrumentation.
Well, what have you observed by looking at microplastics, under microscopic conditions? What do they look like? Are they jagged? Are they smooth? Are they spheroid? Are they all over the place? Like, what been observed?
Yeah, from the naked eye, they look kind of smooth, and then you get close and you see how rigid and malformed they are, and there's like holes, and there's a lot of porosity within these plastics, and they're rigid and jagged, especially if you look at a fiber or even a tire wear particle where it's more cylindrical and kind of looks like a cigar shaped like substance that's rigid in shape. So when you get really close into seeing the physical surface area of it, you see just how like jagged and rigid it is, that from the naked eye it looks perfectly fine. And then you look at it under a microscope and you're like, wow, there's a lot of things happening there where its integrity or its structure or surface area is altered.
And the biofilms you've observed, are they eating the plastic substrate, or is just a good substrate for them to anchor onto as a nucleation site?
I've seen studies that have looked at bacteria communities that utilize it as a substrate. I myself have not done that work. I've seen biofilms develop on plastics, but I haven't done anything to see if they're using them for any purpose.
Okay. I mean, yeah, you can't research everything. Well, very good, Austin. What's the best way for people to find out more about your work and follow you and see papers and everything? Where can they go?
Yeah, I'm really active on Twitter. We have, I guess, academic Twitter, but I use it as a means to talk a lot about my work and research. And my Twitter handle is @Austin_Doug13. And I'm pretty active, and I like to update about my research, my students, the work that we're doing. Really interesting things come out of the laboratory, and that's a really cool way to engage with me and get direct input from me as well, and dialogue.
Okay. Well, very good. Well, Austin, thank you so much for coming on the podcast. It's been a really fascinating call, and thank you very much.
Yeah, thank you for having me. I really appreciated it.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.